Now that we've defined and dealt with some equivalent conditions for normal field extensions and separable field extensions, we'd like to put that together with what we already know and kind of relate normal and separable field extensions back to Galois field extensions. And to do this, we have the following very important theorem. It tells us that if f is a subfield of E and the extension of E over f is of finite degree, then the following statements are equivalent to one another. So the first statement is that E is a Galois extension of the field f, and this is equivalent to saying that E is both a separable and normal extension of the field f. So this relates the concepts of Galois with normal and separable. However, the real use of this theorem, the real strength of this theorem is in showing that these two conditions are equivalent to the third, which is to say that E is a splitting field over f for some polynomial little f in f adjoined x, where f is a separable polynomial over f. So the reason this gives us a lot of strength is kind of this following corollary. Let's suppose that we took little f in f adjoined x to be an irreducible polynomial, and let's require the ground field to have characteristic 0, so that by our work on the previous slides, f is automatically a separable polynomial. Then we fall into condition 3 of this theorem, and what we can conclude is that if E is taken to be a splitting field for this irreducible polynomial, then this field extension, this splitting field, is automatically Galois over the ground field. So this is the real strength of this theorem. If we're looking to construct a Galois extension, we can do that by just taking the splitting field of an irreducible polynomial when we're working over the rationals, and that will automatically give us a Galois field extension. Now let's get started on the proof of this theorem. Let's prove, like we do for any of the following our equivalent proof, let's prove 1 implies 2, 2 implies 3, and then we'll prove that 3 implies 1. Now, throughout the duration of this entire proof, let's write G for the Galois group of E over f. And what we want to note is that G is a finite group, since the degree of this field extension is finite. Now let's work on 1 implies 2. Let's pick, so what we're assuming is that E is a Galois field extension of f, so that f is the fixed field of the Galois group of E over f, so fixed of G. And what we want to show is that E is both a separable and normal extension of f. Now, one requirement of normal is that the extension is of finite degree, and we have that automatically. So what we need to do to show normal is that if we pick an alpha in the field E, that its minimal polynomial over f splits in E. And we also need to show that that minimal polynomial has unique roots. So let's start by picking an element alpha in E, and let's define a set omega to be the set of places that alpha maps to under sigma, where sigma ranges all over the Galois group. So in particular, alpha will belong to omega. Then we'll look at all the places that alpha sort of travels, so to speak, as we apply the different members of the Galois group to alpha. What we'll also define is a polynomial f of x, which is the product of the x minus betas, where beta is an element of omega. So in particular, x minus alpha is a factor, and then we have x minus beta for all other things that might belong to omega. What we want to note is that this f of x is a separable polynomial because it's just the product of x minus these betas, and the betas are distinct members of omega, and omega is a set. So each one of the betas is different, and so by definition, this will be a separable polynomial. And what we claim next is that the polynomial we've defined f of x belongs to capital F adjoined x. The reason for this is because every sigma that belongs to the group G, so every sigma in the Galois group of E over f, simply permutes the roots of f. So if we look at where beta goes, it goes to some other element in the set omega. And so all that's happening when we apply sigma to the polynomial f is that we're shuffling the order in which we multiply these x minus betas inside this product here. We're just changing the order in which we multiply them. But f adjoined x is a commutative ring, so it doesn't matter if we change the order in which we multiply these polynomials together. I suppose I should say E adjoined x is a commutative ring, in which case it doesn't matter the order in which we multiply these things together. And so when we apply sigma to the polynomial f, all we do is shuffle around and change the order of the multiplication, and that means we're not going to change f when we apply sigma to it. So sigma of f is equal to f, and we conclude from that that the coefficients on the polynomial f belong to the fixed field of G. That is, little f adjoined x belongs to the polynomial ring fix of G adjoined x. And here's where we're going to use our assumption that E is Galois over f. That means that f is the fixed field of G, and so we conclude that little f of x belongs to capital F adjoined x. Now, why does this help us? We see that alpha belongs to omega, so alpha is automatically a root of f, and we conclude from this that the minimal polynomial of alpha over f divides f of x. It may or may not be equal to f of x, but it divides it. Since the roots of f of x are distinct, it follows that the roots of the minimal polynomial of alpha over f are distinct, and this means that the minimal polynomial of alpha over f is separable. So that's alpha is arbitrary. That gives us that we have a separable field extension here. And the next thing we need is that f splits. The next thing that we need is that the minimal polynomial of alpha over f splits. But f, by its very creation, splits inside of E. And the minimal polynomial of alpha over f must also split in E because f splits in E. Again, alpha inside of E was arbitrary, so this is going to be true no matter what alpha we chose originally, and we conclude that E is normal and separable over f. And this finishes 1 implies 2. Let's now move on to 2 implies 3, which is actually the easiest of the implications. So what we're assuming is that E is both a separable and normal field extension of f. And what we want to show is that E is the splitting field for some polynomial f in f adjoined x over f, where f is separable. So we're not even requiring that f be irreducible, we're simply requiring that f be separable. So let's begin now, let's clear our definition of omega, and this time let's define omega to be equal to the set of alpha 1 out through alpha n, where these alpha i's form a basis for E as an f vector space. Let's again define a polynomial f of x. This time it's going to be a little bit different. Let's define f of x to be the product, as I goes from 1 to n, of the minimal polynomials of the alpha i's over the field f. Because we're assuming that E is a separable extension of f, each one of these minimal polynomials, m sub f of alpha I, happens to be separable, and by the definition of separability for a general polynomial, this means that f is separable. So we've created ourselves a separable polynomial. Of course, the f that we've defined will belong to capital F adjoined x because it's the product of things inside of f adjoined x, and f adjoined x is a ring. So f of x really does live in capital F adjoined x. And because E is a normal extension of the field f, we know that each one of these terms, the m sub f of alpha i's, splits in E adjoined x. And it follows that f splits in E adjoined x. So what we've done is we've created a polynomial f of x in capital F adjoined x that happens to be separable and splits inside of E. What we need to do is show that E is actually the splitting field for this f. And the reason that we're going to get that is because of the way that we've chosen omega. So we get the field E whenever we have all of the elements alpha 1 through alpha n contained in a field and the field f contained in there. So, I mean, not even actually, we just need all of the elements of omega, and each one of the alpha i's is a root of f. So if we're working inside of a field in which this polynomial splits, we've got all of the alpha i's, and therefore we have all of E. And this finishes 2 implies 3. Lastly, we move on to 3 implies 1. Now this is going to be the hardest proof that we have, and therefore the longest and the most involved. And let's just state what we're proving. 3 implies 1. We're going to assume that E is the splitting field for some polynomial little f inside f adjoined x over f, where this little f is a separable polynomial. But we are not necessarily assuming that this f is irreducible, so we'll have to keep that in mind. And what we want to show is that E is Galois over f. That is, we want to show that when we compute the fixed field of G, that we get f. That's what we want, so let's introduce a little bit of a shorthand for the fixed field of G. Let's let this field be L, and what we want to show is that L is equal to f. And for this we're going to use an inductive argument. So, first of all, if the index sorry, not the index, but if the degree of E over F happens to be 1, which is our base case, then E is exactly the same field as F, is exactly the same field as L, and there really isn't anything to prove in this case, so our base case is somewhat vacuous. So we can assume that E is a strictly larger field than F. Because E is a strictly larger field than F, and we're assuming that E is the splitting field for this polynomial F, we can find an element alpha inside of E that has the following properties. So we want three things to be true about alpha. First of all, we want alpha to be a root of the polynomial F. Second, we want alpha not to belong to F. And last, we want E to be the splitting field for the polynomial which we'll now call G, which is the minimal polynomial of alpha over F. So notice that we need to introduce G instead of little f because we don't know if little f is irreducible. So we want to get our hands on an irreducible polynomial, so we have more theorems for that. And we want to be sure that alpha doesn't actually belong to the ground field. And what we want to notice about this polynomial G, one thing we want to know is that G is definitely going to have distinct roots. That's because G divides the polynomial f, and one of the things we're assuming with 3 is that f is a separable polynomial. So it follows that the polynomial G will also be separable, and G is irreducible. Now, by the way that we found this alpha, we know that alpha does not belong to the ground field f. So if we introduce another field k, which is f adjoined alpha, then this is going to be a field that's strictly larger than f. The reason we need this is we'd like to apply induction. So when we take a look at the degree of the extension of E over k, this must be strictly less than the degree of the extension E over f because k is a strictly larger field than f. Since we can view the polynomial f as living inside the polynomial ring k adjoint x, and we know that E is the splitting field for little f over f, it follows that E is the splitting field for little f when we view it inside the larger polynomial ring k adjoint x. So f is still going to have distinct roots. That hasn't changed by just viewing f as living inside of a larger polynomial ring. And that means we satisfy all of the hypotheses of our theorem, and we can apply the inductive hypothesis. From the inductive hypothesis, we conclude that E is a Galois extension of k, so that the fixed field of the Galois group of E over k is equal to k. With this part proven, what we claim is that if we take the field L and adjoin alpha, that we really get the field k. That's what we're going to show. Remember, the field L is what we're writing for the fixed field of G, and k is f adjoined alpha. Now, what we've just shown, well, the Galois group of E over k is certainly a subset of the group G, the Galois group of E over f. And so by these properties of these inclusion reversing mappings, if we take L, which is the fixed field of G, that's going to be contained in the fixed field of the Galois group of E over k. We reverse the containment. Gal E over k is a subset of G. When we apply fixed to that, it switches the containment, so we get that the fixed field of G is contained in the fixed field of the Galois group of E over k. By definition, L is the fixed field of G, and by what we've just shown, k is the fixed field of the Galois group of E over k, and what we conclude is that L is a subset of k. Now, L is a subset of k, and alpha belongs to k because k is f adjoined alpha, and it follows that the field generated by L and alpha is contained in k. So L adjoined alpha is a subset of k. However, we actually have equality here because k is f adjoined alpha, f is a subfield of L, and so we have f adjoined alpha is contained in L adjoined alpha, and so we actually have equality. L adjoined alpha is equal to f adjoined alpha. So we're on the right track. We want to show that L is equal to f, and we haven't quite shown that, but what we've shown is that when we take L and adjoin alpha, it's the same as if we would have taken f and adjoin alpha. And we're going to use that to proceed and finish off this proof. And now we get to the last bit that we need, the last couple bits that we need. Let's introduce one more polynomial into the mix. Let's introduce the polynomial h, which is the minimal polynomial of alpha over the field L. One last time, let's sort of forget what omega was equal to previously in the proof and define omega to be the set of all elements beta in the field E such that g of beta is equal to 0. So omega is the set of roots in E of the polynomial g. What we want to show is that h is actually equal to g, and from this we'll be able to finish the proof. So what we'll do is we'll argue about the degrees of these polynomials. So let's start by taking beta and omega. And since g is an irreducible polynomial, we know that there's a sigma in the Galois group of E over f, for which beta is equal to sigma of alpha, and this is by one of the theorems in the previous slides, that Goldilocks theorem. Whenever we have an irreducible polynomial and we look at the set of its roots, we can find an element of the Galois group that carries one root to the other. Now, what we want to note is that sigma of the polynomial h, which means take sigma and apply it to all the coefficients, that's equal to h because h belongs to L adjoined x, and L is the fixed field of G. So if sigma is an element of G, and all the coefficients of h belong to the fixed field, then h belongs to L adjoined x. So what do we have? What we want to do is show that beta is actually a root of h. So let's take a look at h of beta. Where we have h of beta, beta we're thinking of as sigma of alpha, so h of beta is equal to h of sigma of alpha. Because h is fixed by sigma, h lives in L adjoined x, h of sigma of alpha is the same thing as sigma of h evaluated at sigma of alpha. The point of applying sigma here to both pieces, both the coefficients of the polynomial and the alpha that's being plugged into the polynomial, is then we can use properties of field automorphisms to sort of factor out the sigma. So we have that sigma of h evaluated at sigma of alpha is equal to sigma of h of alpha. Once we've factored out that sigma, so to speak, then h of alpha evaluates to 0 automatically because h is the minimal polynomial of alpha over L, so alpha is a root of h. So we'll replace h of alpha with 0 so that we're looking at sigma of 0, and 0 is definitely an element of this ground field f, so sigma of 0 is equal to 0. And all in all, that big long equality tells us that every single member of omega, which was originally created out of roots of g, is automatically a root of h. What this means for us is that every root of g that lives in E is also a root of h in E, and therefore g divides h inside the polynomial ring where they both belong, which is inside E adjoined x. From that, we conclude that the degree of h is bigger than or equal to the degree of g. On the other hand, the degree of g has to be bigger than or equal to the degree of h because g belongs to f adjoined x, and we know that f, the field, is a subfield of L. So we could just take g and we could view g as a polynomial that's sitting inside the polynomial ring L adjoined x, and alpha happens to be a root of g. From that, we know that the minimal polynomial of alpha over the field L will have to divide g, and from that, that will give us that the degree of g is greater than or equal to the degree of h. Since we have that both containments, or both inequalities with the degrees of h and the degree of g, we conclude that these two polynomials have to have the same degree. And last but not least, let's use the fact that all these polynomials are irreducible one more time. If we're looking at the degree of the extension of k over L, this is going to be equal to the degree of h. We've just shown that the degree of h is equal to the degree of g, and the degree of g is equal to the extension of k over f. As f is a subset of L and L is a subset of k, we're going to conclude that L is equal to f, because we have f is contained in L. When we look at the degree of the extension from f up to k, it's the same as the degree of the extension from L up to k, and the containment gives us equality of the fields here.